In Chapter 6, we're going to be discussing thermochemistry. Thermochemistry is the study of the heat given off or absorbed during chemical reaction. And nearly all the energy on which we depend is derived from those chemical reactions. Some questions we're going to look at answering are listed here. How do you measure the heat absorbed or released that accompanies nearly all the chemical reactions? How can the delta H, or the change in heat in a reaction, be applied to other reactions? And how can you use this heat information? How can we apply it in real life or interpret it as far as our data? Thermodynamics is the science of the relationship between heat and other forms of energy. Thermochemistry is a study of the quantity of heat absorbed or evolved or released by chemical reactions. In chemistry, we define energy as the capacity to do work or to move matter. We also define heat as energy used to cause the temperature of an object to increase. There's so many different forms of energy out there. Three of the main ones we can look at are radiant energy. For example, electromagnetic radiation, as you see the picture below, the electromagnetic spectrum. That would be all those forms of energy are radiant energy. They travel in waves. The second type is thermal energy. It's energy associated with random motion of a molecule or atom. So it's heat given off. Heat given off. So anything that is hot, for example, the sun, giving off energy. Chemical energy is the last type of energy listed here. It's the energy stored within the structural limits of a molecule or atom. So it is the energy, it's potential energy that's stored within a molecule. The example here are the solutions of zinc sulfate and copper sulfate, and the fact that we can actually derive electricity from these solutions. The energy that we're using to light the light bulb comes from the atoms, the energy stored within these atoms. When we were talking about gases, we mentioned kinetic energy. We know kinetic energy is the energy of motion, and you can see it as Ke or E sub k. It's one of the broad concepts talked about in energy. We learned about the fact that kinetic energy is equal to 1/2 mv squared, where m is the mass and v is the velocity. A second broad concept of energy is potential energy. It is known as E sub p, and is the energy an object has by virtue of its position in a field of force. So in examples will be the energy stored within chemical bonds, the energy of attraction between charged particles, the energy of attraction between a north and a south pole of a magnet. E sub p is determined by the mass times g for gravitational pull and the height here on Earth. So if we sum up all the energies, we come up with the internal energy. Internal energy is represented by the letter U, but as you see on the bottom of the slide, more commonly internal energy is represented by the letter capital E. So we'll be using capital E, even though the book usually you'll see capital U. So the internal energy is the sum of all the potential and the kinetic energies of the particles. From the molecules, electrons, and the nuclei. So the E total would be the kinetic energy plus the potential energy plus the U. So we've got to sum everything up to get the E total. So, but in chemistry, most of the time when we're working in a lab, we're going to be considering our kinetic energy to be 0, because the system that we're studying will be at rest. And it's going to be in a constant position. So the potential energy is 0. So what we will be mainly concerned about is E total, which is the internal energy. If we have an increase in internal energy, it can take the place of 3 forms. We can see an increase in temperature. We can see a phase change, like ice melting. We can also see the initiation of a chemical reaction. These all 3 are started upon increasing the internal energy of a system. This is an oldie but goodie, the law of conservation of energy, also known as the first law of thermodynamics. It states that energy may be converted from one form to another, but the total quantity of energy in the universe remains constant. It's very important to know. Another thing that's really good to know are these units of energy. 1 joule, abbreviated capital J, is equal to 1 kilogram meter squared per second squared. 4.184 joules is equal to 1 calorie, abbreviated CAL. And 4.184 kilojoules is equal to 1 kilocalorie. We will be using these frequently throughout this chapter. When talking about chemical reactions, heat is transferred from the system to the surroundings or from the surroundings to the system. Example, If I touch an ice cube, heat is transferred from my hand into the ice cube. The ice cube would be the system, and my hand and the atmosphere would be the surroundings. The system is what is being studied. In this case, it would be the ice cube. The surroundings are the rest of the universe. The same amount of energy leaving a system or entering a system will be the same as doing the opposite for the surroundings. For example, the amount of energy entering the ice cube will be equal to the amount of energy either leaving my hand or leaving the atmosphere. When we talk about heat, we abbreviate it with a small q. We are addressing energy that flows into and out of a system because of a difference in temperature between the system and its surroundings. So heat is actually a process. It flows from a region of higher temperature to a region of lower temperature. And once that temperature becomes equal, the heat stops flowing. So heat flows downhill. It is important to note the sign of Q. If the sign for Q is positive, then heat is being absorbed and it's endothermic. If the sign of Q is negative, then heat is being evolved or given off by the system and it's exothermic. Then the heat of reaction is the value of Q required to return a system to the given temperature at the completion of the reaction. Another quick review of exothermic and endothermic processes. An exothermic process is a change in which heat is involved. Exo, heat is exiting. Q is negative and the system loses energy to the surroundings. An endothermic process is one in which heat is absorbed. Q is positive and the system will gain energy from the surroundings. These graphs are great representations of both exothermic and endothermic reactions. They show the graph of potential energy versus the reaction progress. If you look at the exothermic reaction on the left, you can see that the reactants start with more energy than the products. So if the products have less energy than reactants, then energy must be given off. The amount of energy given off is equal to the reactants minus the products. In order to get up over the top of the hill, we need a certain amount of energy called activation energy. For the endothermic process, we see the reactant starts out with less energy than the products. The amount of energy absorbed is the difference again from the reactants and the products. And the same thing, this hill is much bigger though. We need a lot more activation energy to get up over the hill and get to the products. Another example of exothermic and endothermic reactions. In the system on the left, we have an endothermic reaction, and the heat is going into the system. On the right, we have an exothermic reaction and heat is leaving the system. So I think these should actually be changed. Okay. So the internal energy, or E, of a system may be changed by the flow of heat or work or both. Taking a look at the first law of thermodynamics, and the little square in front of the E means delta. So the change in energy is equal to Q plus W. Remember that Q is positive, and then if the Q is positive, system gains the heat, and if Q is negative, system loses the heat. So signs are very crucial from defining everything from the system's viewpoint. If work is positive, then work is done on the system. If work is negative, then work is done by the system. A big area of study when it comes to looking at work associated with chemical reactions in the systems would be pressure volume work. It's the expansion or compression of gases. And one example is when you react magnesium with hydrochloric acid. This is what the reaction looks like. You see the piece of magnesium right here that's down inside the hydrochloric acid, and bubbles are forming all over the piece of magnesium. This is what it would look like if we set it up in a flask where the gas could actually flow through the water and be collected in a measuring cylinder. So we're going to try to look a little further into the system and try to derive the delta E equals Q minus P delta V for this. So when it says we're looking at magnesium and hydrochloric reaction in a closed container, you're looking at the drawing that was on the previous slide. I'm not going to walk step by step through this, but you can see the derivation starting with work equals force times distance and ending up with work is equal to negative P delta V and substituting that in to get our delta E is equal to Q minus P delta V. So this slide just shows you the derivation of finding that 1 joule is equal to 1 Newton times meter. So you can take a look at this. The other thing it shows is that 1 joule is equal to 1 kilopascal times 1 liter. And that's actually it for this section. This section is mainly concepts and some derivations. There will be a problem set tomorrow that goes with this section, so make sure you make notes of any questions and be prepared to discuss this tomorrow.